Hi, today's lesson is about interference of waves. So first we're going to look at something called constructive interference, and then we're going to look at destructive interference. We won't have this video link here, but we'll look at that in two-dimensional waves. But we are going to use this website to analyze the constructive and destructive interference. Tons of applications there you can use for physics, so we'll look at that in just a moment. So actually, maybe let's go to that application to begin with, and we'll look at some pulses that are in phase with each other. So I'm just going to bring that up. Okay, so here's that website we can use. So if you look on the right, it says pulse, and the amplitude, we're going to start looking at equal amplitudes, and the phase will be in phase. So if they're in phase, they're on the same side, and as these pulses approach each other, what happens is you can see this yellow line in the middle here. That's going to be the resultant wave, kind of what happens when these two waves add together. And the yellow line is the actual resulting wave. The red and the blue tells you where that wave would have been if there was nothing to interfere with. But the yellow line is the actual product of those waves. That's what you would see. Say if there's two waves passing by each other in the water, the yellow is what you'd see as the product of those two waves. Now if I bring it to a certain point, the red and blue waves are completely overlapping, and it's called total constructive interference, where they're completely overlapping and they're resulting in basically double the amplitude, double up. And then what happens is they continue on, and they pass through each other, and they continue on the same direction that they were initially. They don't bounce off of each other and go backwards or anything like that. They just continue on in that direction after they pass through and interfered with each other. So I'll just play it for a few times so you can just watch it, the waves pass through and interfere with each other. I mean, you can pause the video at any point to stop it where you want to see it as well. You can change the amplitude to show that, waves aren't always equal amplitudes interfering, and so if these are overlapping perfectly, you can see the lines. You've got the blue is 1, we'll call 1 amplitude, 1 length high. The red is 2, and so you can see that the sum of the 1 plus the 2 equals the 3. Okay. So again, these are constructively interfering. Okay, so let's go back and let's just look at a few more things in the notes. Now, here's just kind of a simplified version of those waves. We're using rectangles to show the constructive interference and the adding up, because it's easy to add up the rectangular shaped pulses. It's just easy to graphically show and add them up. So here is before. So if we look at this is before they've interacted at all. This is kind of during the interaction, kind of early on. This is like right in the middle when they're total overlap. And then this one is after they've interfered. They continue on the same motion. You can see, like, if this was pulse A traveling to the right, this pulse A would look the same as it did originally, but it would have passed through that. If we call this one pulse B, they would have passed through each other and moved on. Okay, so here's just a little more detail about adding the waves up. And so we've taken a snapshot in time kind of in the middle where there's some overlap but not total overlap. And you can see what happens. So this is outside of the interference here. Okay, so there's whatever medium is at rest here. And then if you look at this point here, there is no, that wave from the right side is not, it doesn't exist in this little area here. So when we go to add up and see what happens, it's the same as the original. So nothing changes here. Now if we look at this second part here, we see that we have this part of the one wave and then this part of the other wave. And what we do is we're going to add those together. So if you look at it, it would have been something like this plus this. So if you add this height to this height, you get this height here. And so those two waves have added up and constructively interfered at this point. Okay, and then moving along, this point here, there is no other wave. There's only one wave pulse, or sorry, one part of the pulse there, and so that remains unchanged. And then E is outside there. That's the rest position for whatever medium that is. Okay, and you can see, you can kind of see some of that description down here. Okay, so the part where it's constructively interfering is this middle portion, and it's adding, they're adding together. Here's another snapshot. This is when, if they're the same wavelength, which those rectangles are the same pulse length, when they meet perfectly, they will perfectly constructively interfere. Okay? So if you take those two waves and you take those heights, okay, you take this height and you add it to this height, you get this height here. All right, it's perfect constructive interference. Alright, so that was in constructive interference. Now what we're going to look at is what happens when pulses are out of phase. So they're traveling along the medium and on the opposite side. So we have, we have pulse A, we have pulse B, and they're not on the same side of the medium. Picture a string, they're traveling opposite sides of the string. And after they pass, again, they pass through and they continue on the same direction. So this would still be B, and this would be A. They would continue on in motion. Let's look at that application just to see what that'll look like again. So here I can change the phase to out of phase. We're going to go back to equal amplitude. So notice the red just continues on to the right after interference. Blue continues on to the left after interference. But what happens is, again, this yellow is the resulting wave from the combination of the two interfering waves. And if you look at the red on the top, if you look in this middle section, you've got the red on the top and the blue on the bottom, and the yellow is in the middle because there's partial cancellation. And if I kind of drag this along, you'll notice that yellow line, the resulting wave, is somewhere in the middle because those waves are canceling. Part of them are canceling anyways. Until you get to this point where they're completely overlapped, and what do you get? Complete destructive interference. So if you took a snapshot of these two waves interfering at time, it would look like the medium was completely flat because the pulses have canceled each other out. So it almost looks like there's no wave. But the energy from each wave is still there. It's still moving along that medium. The red energy is moving to the right, the blue's energy is moving to the left. But at that moment in time, they're kind of fighting each other. and resulting in zero displacement in that medium. And then you continue on, and you can see that those waves pass through, those pulses pass through each other. Okay, and all unequal, let's look at unequal. So you can see how they add up with the unequal. So we're going to look, just going to bring it to that middle portion there. And you can see when it's unequal how the addition works. So the red is, we'll call that the positive displacement of the medium. The blue, we'll call that the negative. So the red is positive 2. And the blue is minus 1. So what do you get if you add positive 2 amplitude with the minus 1 amplitude? 2 minus 1 is 1. And you can see that this yellow amplitude here is plus 1. So you can see how they combine. And, you know, it still works if you have a positive amplitude and a minus amplitude, right? You just work with the integers. Okay, so continue on. So this is showing that overlapped region from those two waves. If they're the same wavelength, what happens is complete cancellation at that point. You take the displacement from this one, you sum it to the displacement from this one of the medium, and you get the positive phase, the wave from the positive side of things, and you got the part from the negative, and they cancel out. Okay, so that's destructive interference. And you can get partial destructive interference, or you can have complete destructive interference, depending on the amplitudes of the waves, the wavelengths, and how they're matching up. You can see these pulses are equal in amplitude. Usually I can drag this little ruler around on the smartboard, but this is a PDF, so it doesn't work that way. So you can measure things. But you've got that pulse length and this pulse length, they're equal. So when they're on top, they basically have overlaps. If you measure this one and you measure this one, they're equal amplitude, so they'll totally cancel out. And so that's just the opposite of this constructive interference for these two same pulses. You know, you got the same pulse length, so nothing there changes. When they're totally overlapping, you take this one, you measure it, you take this one, you measure it, and you will add that up. And you can find it doesn't just work for the amplitude. So if I wanted to take any point, let's say I want to take a cross section of this point, and let's say I perfectly measured it and I'm finding this point here. I find the displacement from rest to this point. I find the displacement from rest to this point. And to find the resulting at this point, I take this one and add it to this one, and I get this point on the wave. Or maybe you could do this for the entire wave. Take just cross sections to find, say I'm looking here. So I take this point to here, and I add it to this point to here, and I get this point to here. And you could do that for all these different positions on these waves. And if you sum them, you will get this resulting wave. Or if it was destructive, you would get they would cancel out or partially cancel out. Sorry, I missed one down here. So this just shows a few waves passing through each other that they don't have the same wavelength, So it just shows how they interact. So you've got pulse A, pulse B beforehand. You got pulse A, pulse B. There's some partial interference in this area here. Right? You can see this is part of B. This is part of A. Now, what happens? The result is this solid line here. These dotted lines are kind of imaginary. When they're interfering, they're producing this wave you see, this constructive pulse here. Okay, and then it goes on to show them as they pass through. I just need to take a look. Was A the small one or the big one? A is the small one, B is the big one. So if I label them here, okay, this is A, and then this is B. And at this point here, they're overlapping to make this larger pulse at this point. So that's where they're constructively interfering perfectly. And then what happens is as they pass, you've got A continue on to the right, B continue on to the left. And you know, if you take a measure of the amplitudes, it's easier if I have a ruler, but so if this is 0.75, 55, 0.6, 0.65, 0.7, 0.8, around 0.8 amplitude. And then if I go to here across, this one's a bit harder, but let's say that's 0.55. So when you add the peak of those two amplitudes here and here, if we go up to the top, you should get 0.8 and 0.55. Okay, so the maximum approximately should be 1.35. Let's check. So if we go across, yeah, ish. I mean, if I had a ruler out and was doing this perfectly, it should match up perfectly, but there's 1.3, 1.35, so somewhere in there it seems to work out. So that's constructive interference of two pulses that have different amplitudes, and they actually have different pulse lengths too. So it just shows them adding up as they pass through each other. So what we've been looking at for pulses works just as well when you look at continuous waves passing through each other. But the waves, basically there'll be patterns, because as the waves travel, they'll continue to pass and make these different patterns. So here's two waves. You got wave 1 and wave 2. Picture wave 1 traveling to the right. Picture wave 2 traveling to the left. And what happens if you take the basically snapshots in time, they could be constructively interfering or destructively, or partial constructive and destructive, depending on how they're overlapping. So this first snapshot in time, you just take the positions and see what is happening at those positions. So let's look at this here. So they're both at rest, so the resulting wave will definitely be at rest. Let's take this point here. Well, that's maximum amplitude, that's maximum amplitude. So because they're both positive and they're both their maximum, you will get complete constructive interference. And you look here, oh, that's at rest, So this will be at rest. Then you look here. Well, that's negative, and that's the maximum displacement in the negative. Same here. They will both add up on the negative side perfectly. Rest, rest, so that's at rest. Max, max, they will sum to the max. Rest, rest, rest. Destructive, total, negative, negative, so they'll be constructive but on the negative side. And you can continue on, and this is perfectly, this is when they would be perfectly constructively interfering. All the positives are adding up. All the negatives are adding up but on the negative side. And that would continue, that pattern would continue on. Okay, so what happens in the next point is it's kind of the opposite snapshot. You've got rest, rest, rest. But then if you look at this next kind of little snippet here, you've got positive, negative, cancel. Okay? And you got rest, rest, rest. Then you've got negative and positive, cancel. Rest, rest, rest. So there's 0 there too. Positive, negative, cancel. So if you add, it doesn't matter where you pick on the waves. I could pick something like right here, anywhere on the wave. That's positive, like that's about half of the amplitude. And then if I look at the other part at this, on this other, the second wave, that relative position, it's negative about half. So what do you get if you have plus a half and minus a half? You know, they cancel to 0. So it doesn't matter where you pick. I could pick here, and that would match up with here. They cancel. Complete destructive interference. And that's called two waves being 180 degrees out of phase, so perfectly out of phase. All right, so this is a technology you probably are familiar with, and maybe you don't, you've probably never really understood how it works before, but I'm sure you've heard of noise canceling headphones. So it's a pretty good application of this understanding of constructive and destructive interference. So essentially what the headphones are trying to do is cancel out any unwanted noise. So they're reading the incoming noise from outside of the music you're trying to play, and what it does is it reacts and it creates these other waves to totally cancel it out. So here's, for example, an external source coming in. The speaker or headphone will react and produce waves that will completely destructively interfere. So essentially make that flat line, so your ears are not picking that up at all. They're only picking up the music that's intended for your ears. So that's just one really interesting little application, a useful application of constructive and destructive interference. In this case, it would be destructive interference. Okay, so that's constructive and destructive interference. The next lesson is going to be on standing waves, and basically it's a continuation with interference. But there you go. Talk to you later.